Okay. Yeah, thank you. Yeah, thanks, Matt, for the introduction. I am also Matt Lester. I'm the corrosion control specialist of the lead and copper unit. I'm going to be going over session 8 of water treatment 1 today, which is the corrosion control section. What I'll kind of be talking about is corrosion itself, kind of the background, the history, the understanding of what we know of corrosion. Kind of roll that into corrosion control treatment and things like that, different indices that we use to analyze corrosion control, and then kind of roll that then into kind of the background of that, right? Lead and copper rule and things like that. So we'll briefly hit on some of those things as we go along. So I think I got you for an hour, so here we go. So first thing I want to do here is kind of run through acronym, definition slide here. Some of the things that are, kind of good to know that you'll kind of see reference throughout this presentation. So the first four, things there, PB, CU, SO4, and CL, those are kind of your compounds, your actual elements themselves. Pretty straightforward if you've taken kind of general chemistry in the past. Okay, the three at the end there are your lead and copper rule, or LCR, corrosion control treatment, CCT, and then optimized corrosion control treatment. Okay, and we should be talking about each one of those as we go through the presentation, but just so you know, that's there. All right. So as I said, the first kind of thing I wanted to get into is the corrosion science. All right. Essentially, what is corrosion? What is this complex kind of idea that we talk about it? Well, you might have a better understanding of it than what you realize. So to get into it, let's start with the definition of corrode. Corrode is basically destroy or damage metal, stone, or other materials slowly by chemical action. Okay, and then corrosion is essentially just the process of that corroding. Okay. Corrosion itself is caused by oxidation. Now, you might not necessarily understand what oxidation is yet, but we'll touch on that in a moment. But, I think the slides down at the bottom, or the pictures down at the bottom, really kind of, give that idea. You probably dealt with corrosion your whole life, whether or not you really realized it or not. But it's everywhere. It happens pretty much, all the time. It's definitely very prevalent in the materials that we look at every day in the drinking water program, metals specifically, right? So we got a couple of things there. That image on the left, we have that chain. So we have a new chain kind of down there at the bottom, right here. And then you have this rusted chain up here at the right, or at the top right. This, again, you've probably seen this your entire life, whether that's on cars and things like that. That is just another form of corrosion that's occurring. You got this middle image here. Looks like it's just some copper pipe that's going through this oxidation process. You even have some water here. So whether that's a pinhole leak or something else, or something's even dripping on that copper piping, but you're having some, heavy corrosion. You're even seeing some interesting color formation there as that copper itself corrodes. Just, kind of like Lady Liberty, right? Same kind of concept there. Copper, going through that corrosion process, that oxidation process. And then you got one to the right here, some form of metal or steel pipe that has what we'll talk about later, but tuberculation, right? So you're having some corrosion, some oxidation of that piping, and you're getting these buildups of that material type, okay? So that's kind of the background of that. So I kind of use that in that terminology, oxidation, right? So when we talk about oxidation, there's also the corresponding term reduction. Okay, and essentially, if you've taken general chemistry, that's just kind of these reactions that we get in those chemical reactions, right? So what is oxidation itself? So oxidation is the process where a substance either loses one or more electrons, gains one or more oxygen atoms, loses one or more hydrogen atoms, or increases in its oxidation state number, okay, or state. Reduction is essentially the opposite of that oxidation. And what we're talking about there, and why those things go together, oxidation, reduction, is these things that we typically refer to in the chemistry world of redox reactions, okay? And this is kind of summarized here in this kind of concept down here. So you have a substance, you could even have multiple substances. There's a whole, chemical reaction that's going on. You have this, two-sided arrow here, which means essentially that the reaction can either go one way or the other way, depending on what that is. And then it will go to this other, substance plus one, and the electron. Okay, so it's this kind of broken down style of substance. Okay, so whatever that might be, and we'll talk about some examples of that, but maybe that substance is iron. Okay, and going through some sort of chemical reaction, whether it's just with oxygen and water or with some chemical, you're going to then have these substances that are of a lesser oxidation state. It's going to be driving off that electron, and now it's going to be in this reduced form of or oxidized form of iron. Okay, and obviously that can work with any sort of metal. It's all dependent on what that actual chemical reaction is. Now, as I briefly hit on, this arrow is two-sided arrow, so the reaction can either go right to left or left to right. Now, in most circumstances, what we're talking about in our world, when we're talking about corrosion specifically, you're dealing with the left to right process. So a full style of material going to a lesser style of material, okay, driving off that electron and being in this kind of reduced state of itself. All right. So this is kind of just kind of a look of what that corrosion kind of looks like. All right. Electrochemical reactions. Essentially what we're talking about is you're having an anode and a cathode. Okay, and I want to use one phrase here that is very good for memorization, kind of understanding it, is an oil rig cat. So ANOILRIGCAT. So AN standing for anode, oil standing for oxidation is loss, RIG, RIG, standing for reduction is gain, and then CAT standing for cathode. Okay, and so I just really want you to have that little memorization in the back of your head, because I think it is important. It's a really easy trick to understand that kind of chemical background. So again, N, oil rig cat. So AN, anode, oxidation is lost. So anode is the one that the electron is being lost on. Okay, where cathode is where that electron is being gained. Okay, so reduction is gain. So oxidation is where you're having that loss of the electron and you're losing this material. So if you remember that equation that we had on that previous slide, you're having that substance. In this case, it would be pure lead. Lead S is solid. Okay, so that solid lead component is the anode in this situation. The reaction is going to the right, like we talked about, to be a lesser state of lead. Okay, so it's no longer lead solid. It's now just a pure lead particle, lead molecule, I should say. And then you're having that electron being driven off. You're actually having two electrons being driven off. Okay, so you're losing that lead piping, that solid lead pipe wall, and you're driving it into, well, the solution, into water in this case. And actually, because there's only one type of material, your cathode here being your water. Okay, so you're having your own reaction with water where it's comprised of H2O, it's comprised of hydrogen atoms and oxygen atoms, and you're forming, these chemical reactions that are just naturally occurring. Okay. So again, lead is being oxidized here. Now, there's other things that can be oxidants. We talked about oxygen in the previous discussion. Yes, oxygen is an oxidant. You also have other things like chlorine, and other potassium permanganate and things like that. Usually oxygen is part of those molecules, but you can have an increase in that oxidation ability. Okay, so that just gives you a little bit of background. Next thing is just kind of a different look at what we just looked at. This time it's not a lead pipe, it's an iron pipe. But this, again, just kind of gives you a different look. So iron down here, you're having this anodic site to this cathodic site, maybe further downstream or even just the water itself. But again, that iron is being stripped away because you're having this chemical reaction with water. You're having this oxidation here. That iron is going away into this reduced state. It is no longer, solid iron. It's combining, in this case, with oxygen that is just naturally occurring in the water and is forming rust. And this is what we call tuberculation, like we talked about on that second or third slide in, right? So you're having that rust, and it's just basically falling out of concentration. It's falling into and precipitating out of the water and just depositing itself on this iron wall in this form of ferric iron. Same equation down here that you'll just kind of understand there. That iron, that solid form of iron, that pure substance, whatever it's comprised of, that alloy, metal, whatever it might be, going into that reduced state, that oxidized state, right? So Fe2 plus, it's now aqueous because it's going into the water column. You're losing some electrons here. And then again, you're having this reaction, this naturally occurring reaction with water, okay? So you're having oxygen being driven off or maybe forming more water molecules. But that's just the general idea, okay? Here's just another look of that. And yet again, just another look of that, right? So this is the real world example of that. You're having tuberculation here. That is an iron pipe or steel pipe of some kind. You had some oxidation over time, just naturally occurring with the water or whatever other chemicals might have been in that water. And you're having this buildup of, ferric or iron oxide, I should say. Okay, so that's just that, and it's just getting into the water column, precipitating out, and forming these tuberculations. So what is tuberculation? Tuberculation is, well, what we just saw. It's those clumps of, iron oxide that kind of form in these ways, right? So there's various forms of that. And essentially what we want to talk about is, you can have these different layers, these different makeups of what that iron is. So you can have crustable or friable, this kind of style that could be comprised of hematite, carbonates, silicates. Those are the things that might be driving that iron oxide, that iron, combination, right? That iron compound. You can have a shell that might be more brittle. So you could have magnetite, or you could have your actual core, maybe of that initial kind of stage of that you're having that iron oxide, right? So ferrous hydroxide, siderite, phosphates. Those are those things that might be driving that reaction right off the bat. And so you can see here just kind of the same kind of thing. This might have been the initial pipe wall surface. Now you're having this loss of metal, and now it's building up. Usually this is probably downstream, but once it deposits downstream, then you can still have those reactions going forward. Okay, so a couple of terminologies that I used. Friable means it can easily crumble apart. It'll just come apart in your hand. Or brittle, it's although hard structure, it will eventually break if you use enough force on that. So friable is a little bit easier. You can probably just crumble it in your hand. Softer kind of oxidation versus brittle, which is your kind of firmer, harder. Maybe you hit it with a hammer instead or whatever to knock it loose. Okay. So as we talk about corrosion, there's other things that might drive corrosion here. Instead of just the water column itself, water coming into contact with the metal surface, you also have this concept of dissimilar metals. All right, and dissimilar metals is essentially this idea of different levels of activity. Okay, what is more or less likely to give up that electron? So if there's a type of metal or a type of substance in general that's more or less likely to give up that electron, that's the one that will likely lose that material, right? So you're giving, if it's on that high activity level, it's more willing to give up the electron than the one that's lower on that activity level. That makes sense. So it's more willing to keep. If it's lower in that activity level, more likely to keep that electron versus higher on that activity level that it's more likely to give away that electron and therefore lose that material because it no longer is binding to that solid. Okay. And so this is just kind of a, generic kind of scale here that we have, where gold is on that very least active. So it's less likely to give away that electron versus magnesium, which is on a very high level of activity. And we'll talk about this kind of concept in a little bit later, but these kind of last three, well, actually last four is a great example of what we deal with a lot. And when we're talking about, hot water tanks, okay, you have your magnesium rods, your zinc rods, you might even have aluminum rods, okay, and anode rods that you put into a hot water tank to basically protect that iron or steel container that is, the actual tank itself, okay. So you're putting those things in, you're putting those anodes, those sacrificial anode rods, you're putting them in to be that sacrifice, that sacrificial anode, more willing to give up that electron to then protect that thing that's on a, lower activity level, steel or iron in this case, okay? So we put these things in here, knowing full well that they're going to corrode, they're going to degrade over time to protect these things from this concept of dissimilar metals and corrosion in general, okay? And we'll touch on that kind of concept quite a few times as we go through it, because I think it's a really good example, something that we deal with on a regular basis, but we don't necessarily always think about it, all right? So this is just another look at that corrosion from dissimilar metals, okay? So you have a couple different combinations here. So you have aluminum bolt with a copper nut, copper bolt with a steel nut, steel bolt with a copper nut, okay? They were put into some form of solution to kind of drive that reaction, because if they just sat by themselves in a completely dry situation, nothing would really occur. You need that electrolyte. We'll talk about that in a little bit. You need that electrolyte to kind of drive that reaction, okay? And so what's essentially going on here? We can flip back and forth between the previous slide or not. So you have that aluminum bolt and that copper nut, all right? And it looks like, you can kind of tell it definitely looks a little bit more oxidized here. And so let's just double check that makes sense. Going back, you have aluminum that's on your more active side than your copper, right? So your aluminum is more likely to corrode than the copper is in this situation. So it's a little hard to tell maybe in this picture, but you'll just have to take my word for it. The copper is, kind of more, better kept in shape than the aluminum that's starting to degrade pretty heavily. You can see it a lot easier here in this picture, much better lighting. You can see the copper here with the steel nut. Copper looks relatively unaffected comparatively to the initial picture, where the steel nut is, clearly there you have some, pretty intense metal loss here. Okay, same thing kind of down here. Again, maybe not the best image, but your copper here, nut looks relatively untouched. There's no obvious material loss, where your steel bolt is, clearly heavily corroded at that point. So that's just kind of getting into that concept of dissimilar metals. Again, there's a lot of examples of that, even down to, copper with lead solder and things like that, or, two different pipes that are touching each other and different components that are in your well houses and whatever that might be. But it's always important to keep those things in your back of the mind, because this is real world. This does happen. You can have issues. You can have premature failure if you put two dissimilar metals together, that are, kind of conversely effective on the activity scale. All right. So always keep that in the back of your mind. So next, we're going to roll into kind of concepts of what is corrosion itself in terms of what we deal with in drinking water. All right. So so the effect of chloride and sulfate on lead corrosion. Now, although we're starting to understand a little bit better, it's still not completely understood at a fundamental level. We understand certain aspects of it, but essentially, the reason I say it's not understood at a fundamental level is because it's really only kind of driven through empirical data at this point. Empirical meaning real world or lab type sampling, something that we've seen, we can demonstrate it, we know it's occurring, we just can't necessarily pinpoint exactly why it's happening, okay? So, chloride itself is at least thought to form complexes with soluble lead, which prevents the formation of insoluble lead oxides. Okay, so what that's essentially saying, soluble meaning it's going into the water solution, insoluble meaning it's going to kind of stay as a particle or stay as that, that real thing that you can either filter out or it'll precipitate out or it'll form these compounds, where soluble will stay in solution and just kind of float into the water column just like anything else. Okay, so those chlorides might be, kind of combining with, well, not might be, they are combining with the lead and staying soluble instead of, again, going insoluble, oxidizing, falling out of, precipitating out of the solution of water. Okay. Sulfate, on the other side, is thought to promote the formation of solids. Okay, so kind of that the converse almost of that, but it's also driving those reactions to have that lead then build that insoluble form in whatever that state might be, or that combination of lead. Okay, so you're kind of having these converse kind of concepts here. They're directly contradictory to each other. All right. So in addition to this, chloride may also be increasing the transport of ions through the passive layer. Okay, so what that's saying, even if you have a passivation layer, we'll talk about that, but if you have calcium carbonate or if you have some phosphate scale that's on your pipe, high chloride concentrations in your water, those ions that are coming off the chloride might still affect corrosion rates, even though you have a passivation layer. Okay, even if it's, whatever, it's there, it's meant to protect that pipe wall. Okay, well, again, we'll talk about passivation layers in a little bit, but that concept of chlorides can be affecting those corrosion rates. Okay, and we'll talk about CSMR, which is your chloride sulfate mass ratio, in a little while. So, impact of water characteristics on lead corrosion. So again, this is empirical kind of concept here. This was from a specific study, but for the most part, we understand these things to be true. Again, you might not be able to directly point to them in terms of scientific manner, but for the most part, these things are pretty solid. Scientific technology or standpoint. Okay, we know these things, right? So increase in pH should be greater than 7.2. How is that going to affect the corrosion rate? It's going to decrease that corrosion rate. If you increase the chloride, you're more likely to increase that corrosion rate. If you increase sulfate, you're more likely to decrease the corrosion rate. Okay, alkalinity that's less than 50 milligrams per liter as calcium carbonate is more likely to increase your corrosion rate. Now, there's also an aspect of there where too high of alkalinity can also increase your corrosion rate. You have increase in dissolved oxygen, you're more likely to increase your corrosion rate. Increase in hypochlorite is more likely to increase your corrosion rate. And increase in orthophosphate is more likely to decrease your corrosion rate. Now, this is really complex, and obviously all these things can interchange, and they can change whether it's treatment or a new well or all these things. But the general idea here is what I want you to get away from this slide is that corrosion control treatment, or corrosion in general, is very complex. There's not just one be-all end-all factor that we need to pay attention to. It's a very large kind of concept here, that even if one of these changes, it can affect the rest. Okay, so if we increase that pH, or if you decrease that pH, you can affect those corrosion rates for all of those other things there. So it's just a very complex thing. I think it's important that you understand there's a lot going in here. And I could probably even add more to that list, but that was specifically from only one presentation, okay, or one research paper. So factors impacting iron corrosion, scale buildup, and iron release. So same kind of concepts here. I'm not going to get into all of these, but for general ideas, pH in a specific range if you're going to start increasing those pH ranges, you're more likely to decrease corrosion and build scale. Okay, so you're going to have less iron release because of that. All right, so that's kind of how we're reading this chart here. We'll go to the next one as well. Dissolved oxygen is another good example. You're more likely to increase that corrosion rate. Scale buildup is somewhat dependent. You know, again, because there's so many other factors here, there's other things that drive it. Fe release, again, dependent. Most likely, you're probably going to be increasing your iron release in that regard if you're increasing the dissolved oxygen. And again, all these factors, and it just kind of, it's important to understand that this is complex, and even one change, one difference can affect kind of the rest. And basically corrosion is complicated. So that's what I want to keep in the back of your mind. All right.
Hey, so, Matt, before you go on, can we do a poll question?
Yeah, absolutely.
All right. This poll question is going to kind of go right back to the beginning of this webinar session. I'm going to launch it right now. And just a quick question for you. What is corrosion caused by? Remember, if you're looking to get continuing ed credits, then you do need to answer the poll questions. And we will share the response to this poll question when we close the poll. All right, up over 90%. We'll let this run here for about another 20 seconds. If you do not need continuing ed credits, you can certainly ignore the poll questions. All right, 96% looks like where we're going to stall out. 52 out of 54 of you responded. Let me close this poll here and share the results with everybody. So Matt, the overwhelming response is oxidation.
Very good. That's I appreciate that we're getting good responses on that. Yes, oxidation is correct.
Good. Hey Matt, can we also get the N oil cat rig acronyms again for the for some of the operators on the chat?
Yep. An oil rig cat. So AN standing for anode. Oil standing for oxidation is lost. Rig standing for reduction is gain. And cat standing for cathode. So if you can just kind of picture that sentence, you're basically going to draw a line right in between oil and rig. Draw a line right down the middle of that phrase. And then you have your left side, which is N oil. And then you have the right side, which is rig cat.
Perfect. Thanks, Matt.
Yep. All right. We all set to jump back in then?
Yep. Take it away.
All right, so now we're getting into corrosion control. We just kind of have our background of what corrosion is. Now to get into corrosion control itself. All right, so preventing corrosion. All right, there's kind of two main forms that we're looking at this. We have cathodic protection, and then we have passivation. So cathodic, which you might kind of already speculate a little bit with what we just talked about in oil rig cat, right? So you have two kind of concepts of cathodic protection. Active or impressed current, which is essentially you're applying voltage, you're applying free electrons to that site, so that your whatever your anode itself, your anodic site, is less likely to give up those electrons because there's already plentiful electrons because you're applying a voltage, right? Or you have your passive or galvanic, and this is what we were talking about earlier with the hot water tank. You have that sacrificial anode, right? Put that anode rod in that hot water tank. It's going to have this high reactivity rate or activity rate comparative to that low activity rate or hopefully that your material is. Otherwise, it's not going to work very well, right? So you're going to have that thing, whether it's magnesium rod or a zinc rod or an aluminum rod, you're going to protect that iron or that steel piping. Okay, so those that kind of concept. The other side of that is that passivation. So essentially passivation, which we've already kind of referenced a little bit, is essentially you're creating a coating, a surface, if you will, around that material. So you're no longer coming in direct contact, those things that want to cause the corrosion or cause the excessive corrosion, you're no longer allowing that to come into surface with the actual material that's being corroded. So in our circumstance, our life of drinking water, you're talking about the pipe wall having a passivation layer in between that with the water column itself, not allowing that water to come direct contact with the pipe wall, because you're forming calcium carbonate scale, or you're forming phosphate scales of some kind, or maybe you're even forming silica scales. Okay, so it's that kind of concept that we're talking about. All right. So getting into that active or impressed current, this is just kind of an example of that. Essentially, you're having some electrical current being driven off, driving through an anode bed, and basically protecting that. Now, I don't know how much we deal with this in the drinking water world. Maybe a little bit with elevated storage tanks and things like that. I know that this is probably more common in your gas industry. That they're trying to protect those lines with an impressed current. Okay, but again, I'm not sure how common it is really in the drinking water world, except for a few examples like an elevated storage tank or something along those lines. All right. Again, the more common one we're dealing with is that passive or sacrificial anode kind of concept. All right. And so this is exactly what we're talking about here. So if you had an iron pipe here, or iron, imagine this is a hot water tank. You're having this iron chunk here, solid iron, that's nearby this zinc, which is lower or higher, I should say, on that activity scale. So it's more likely to drive off those electrons, protecting that iron, losing the zinc. But at the end of the day, we don't really care, because that's just something that we want to replace, or we're able to replace, where we're trying to protect this iron here. Now, the converse of that, which would be a bad example in most circumstances, you're having your copper and then versus your iron, where the iron is more likely to give off the electron than the copper is, which is losing that material itself, losing that solid iron, losing it into suspension to the water. All right. So again, driving into this this passivation kind of concept, where we're essentially creating that liner, surface, if you will, with this pipe material. So if you remember from one of the first slides in this presentation, we were looking at this exact equation where you're having a lead pipe, solid lead. Here, solid lead going into one reaction, you're having that electron driving off, you're having the lead material itself driving off into the water, and this is your equation with water as well. Okay, so you're losing that lead in this situation. Now, we go to here, which is just kind of, animation. If you put in this new, this darker ring that we just added in, that's that passivation layer. Again, whether we're adding a phosphate or something of the kind, you're protecting now that lead surface, like we were right here. Lead surface coming in direct contact with water, no longer coming in direct contact with water. So you're no longer having those same reactions. You're having that passivation layer that keeps that water away from direct contact with that pipe wall surface. Okay. So, which we were kind of talked about earlier, I alluded to earlier, to have a corrosion cell, to have corrosion kind of forming, you need essentially three things. Okay, so you have an anode, a cathode, and electrolyte. In the water world, we have that pretty much always, right? Whenever water is there, you're going to have that potential for that corrosion cell. So you have anode, cathode, electrolyte. All right. So one thing that's losing those electrons, one thing that's gaining those electrons, and then the electrolyte that's kind of driving that process. So what we're trying to do, again, is form that passivation layer, keep those things out out of direct connection with each other, out of direct contact with each other. And to do that, to perform passivation or passivation layer, we use kind of three different kind of main concepts. Calcium carbonate scales, which is typically what we call more, naturally occurring, injection of phosphate, or injection of silicate. All right, we'll dive into those examples. So what are we talking about here? So if carbonate is present, lead carbonate minerals can passivate the lead surface. All right. So on the left here, I think is a good concept of this. You can kind of see some scale, maybe it's a little bit lighter. So you probably have some calcium in the water. You're forming some compounds with the lead, but you can still kind of see those gray specks in there. It's not all that, well passivated. Where if you're talking about orthophosphate, you're forming, these larger complexes, more durable, less soluble complexes than the calcium carbonate. You're going to form a more uniform passivation layer. Okay, so you can see that on the right here. This is orthophosphate. Even it's almost a little yellowish or orangish. It's got that kind of cream look. That is a passivation layer of orthophosphate that now you don't have those gray specks. You're not having that direct contact with the water and the lead pipe itself, okay, because you form that solid, firm passivation layer of orthophosphate. All right. So diving into what phosphates are a little bit, or corrosion control inhibitors in general. So you kind of have two concepts, phosphates and silicates. Now I'll say right now, we'll talk about silicates for a moment, but there's no drinking water supply in the state right now that's using silicates, at least to the best of my knowledge. Okay, not ultra common around here. Phosphates, on the other hand, they're fairly complex. Not all of them, they're not created equal. They're very different in that regard, in terms of their compositions, from even manufacturer to manufacturer to style to style. So orthophosphate itself is used for corrosion control. It's that corrosion control inhibitor, we typically refer to it, where polyphosphate is used as a sequestration, compound. All right, so we'll talk about that. Sequestering means basically to surround. Orthophosphate is actually that building that passivation layer. Polyphosphate doesn't build a passivation layer the same way. It surrounds molecules and keeps them in suspension of water. Please note that polyphosphate is essentially just meaning that it's a string of orthophosphates, and eventually those strings will eventually break down into individual orthophosphates. All right. Silicates are also not created equal. They're fairly complex. Chemistry is definitely a little bit trickier. They're typically more expensive to manufacture. That's why we typically don't see them. They're also not always as effective, and it's very specific. They can be used in specific scenarios for that water chemistry. Part of the reason that they're expensive is essentially going through this bullet point here. Silicon dioxide and sodium carbonate react when molten to form sodium silicate and carbon dioxide. So that's that process. It takes an immense amount of heat in this process to actually make that silicate compound. Okay, because of that, they're used in things in hot water condition, whether it's boilers, automotive antifreeze, things like that, because they're this more robust kind of compound, even though they're not necessarily as good of a corrosion inhibitor when we're talking about just drinking water itself. Okay. So as I said, for phosphates, there's kind of two concepts, poly versus ortho. Poly here is this string. It's that sequestering agent. It's surrounding that ion. In this case, it's calcium. You could also put in iron or lead, or you could put all these things in here. So it's keeping those things in suspension. It's and keeping them down the line, okay, and keeping them in the water column itself. Where orthophosphate is more likely to bind with those pipe wall surfaces and create that passivation or that protective scale layer. So it's more that corrosion control. Again, not coming in direct contact with the pipe wall surface. All right. So phosphate products, again, when you're looking at a chemical supplier or whatever, there's various forms of phosphate. So you have orthophosphate, polyphosphate, and then most commonly you're going to see some form of a blend. No matter what chemical supplier you're using, that's usually what they have here. So 100% orthophosphate, which is like phosphoric acid would be a good example of that. or a polyphosphate, 100% polyphosphate, like a hexametaphosphate is a good example of that, or a blended phosphate. That could be any of your, typical, products that has, some number after it, right? So orthophosphate, again, it's a single chain. It's just that orthophosphate molecule. It can come in powder or liquid. It's meant for corrosion control. It's a very simple test for the titration kit. You can do it handheld metered. You can send it to lab. It's pretty easy. Polyphosphate, it's that multiple, chain of those orthophosphate molecules. We'll actually go back to this slide for a second. These are individual these little circles here are individual orthophosphate molecules. That's what I mean by a chain. So it's just strung together, okay? Polyphosphate can also come in liquid or powder form. It's meant for typically iron sequestration or manganese sequestration in those regards, keeping those things in suspension, keeping them in the water column. Breaks down or reverts back to orthophosphate. Again, it's those strings, it's those chains. They break down to orthophosphate. These require to sample for it. It requires digestion. Typically, what we're talking about, I think we talked about it in a little bit. You're taking your phosphate, you're measuring total phosphate, and then you're basically subtracting your orthophosphate away from it, that sample, to get your actual polyphosphate, residual or dosage, whatever that might be. Okay, and then blended phosphate. The idea is kind of to achieve multiple goals here. It's a combination of poly and ortho. They can come in all sorts of, styles and blends and whatever else. Now, what I want to talk about this point a little bit briefly, used to achieve multiple goals, although that's somewhat true. You can have some sequestration and you can have some corrosion control treatment out of that. We do know that polyphosphate comes, kind of affects orthophosphate's ability to form passivation layers. So we do know that. So although, they might be the best of both worlds, it's never really the best of both worlds. Okay. So phosphate levels, always make sure you're meeting your NSF max dose. You also have concerns with wastewater limitations. You don't want a ton of phosphate or phosphorus in our wastewater, because then it affects our lakes and streams and our ecosystems and all those things. Okay. Typically, although every system's different, we see corrosion control treatment kind of that maybe 1 to 2 parts per million orthophosphate residual. But again, it's dependent on the system. Some people have 3 or 4 parts per million, and some people have 0.5 or even 0, depending on what your treatment is. Okay, sequestration is all dependent. There's also limitations with iron there. Okay, so this is just kind of touching on what I just talked about with your, actual handheld kits. You're taking your orthophosphate residual very easily. You can also do total phosphate with some digestion there, and then you can get polyphosphate by essentially subtracting those two together to get your polyphosphate. Now, down at the bottom here, I also want to point out, you make sure that your units are proper. So 4 milligrams per liter is not the same thing as 4 milligrams per liter as P. So as PO4 or as P. Okay, these are basically just unit conversion kind of concepts, but essentially it has to do with your molecular weights. So make sure you are reporting it properly. You are getting the right values here. You're reporting them to Eagle appropriately. Okay, so you're not overfeeding or underfeeding. You're meeting that whatever you have. So make sure you're getting your units proper, milligrams per liter of PO4 as PO4 or as P or as phosphorus in that regard. Okay. So these are we're going to talk about indices briefly. These are just various forms of way that we might be able to determine the corrosivity of water. So LSI, or Langley Saturated Index, is essentially an indicator of the degree of saturation of calcium carbonate in the water. And it goes by that equation there. Okay. So LSI, a little bit more complex, but it's just an indice. It's not the be all end all, but it can be maybe an indicator that there could be a more corrosive event or more corrosive water going on with that. Okay, so basically calculated using pH, alkalinity, calcium, total dissolved solids, or TDS, sometimes we refer to, and temperature of the water. Okay, essentially what you need to know here, if it's negative, Water may be undersaturated in terms of calcium carbonate. So basically, if it's negative, that negative LSI value means it's not likely to form that natural passivation layer, that calcium carbonate scale. If it's positive, you're more likely to form a calcium carbonate scale. Okay. Forming scale is a good thing, like we talked about, building that passivation layer. Okay. And this is just a chart. There's lots of data that goes into this, or, you know, science and research papers and all that go into this. This line right here is your equilibrium state. So if you're going with a negative LSI, it's going to go this way on that dotted line. So you're having that potential for scale release or scale instability. And if you're going up on that dotted line, you're actually having some scale formation. Okay. There's also an online calculator that you can punch your values in if you're ever curious about your own LSI for your community. But again, isn't the be all end all at the end of the day. If you have a negative LSI, it doesn't mean you're having corrosion issues. If you have a positive LSI, it doesn't mean you're not having corrosion issues, but it's an indice that we might use to speculate some things. Another one, we briefly touched on it, chloride sulfate mass ratio. Essentially, you're taking the concentration of chloride over the concentration of sulfate to get your CSMR value. And CSMR is built on this empirical kind of knowledge rather than that instant or that actual proof fundamentally that we don't fully understand yet. So again, what to take away from here, 0.58 and greater means that you're less likely to have corrosion issues versus less than 0.58. You could have some issues there. Okay. Or I'm sorry, vice versa. I misspoke there. Greater than 0.58 is the potentially corrosive situation versus less than 0.58 is not corrosive. Okay. Again, that chloride sulfate, that chloride is that factor that might be negatively affecting your corrosion control versus sulfate that's typically considered more helpful towards your corrosion control. Okay. LSI or LSK, I should say, is another indice, kind of dealing with the same kind of concepts here. Not going to get into a ton of details, but you're dealing with equivalent concentrations, equivalent masses here, or weights, I should say. So you're having this equation here, basically less than 0.8. Chloride sulfates will not interfere with natural film formation. 0.8 to 1.2, while they might interfere, and then greater than 1.2 is that they're likely to be interfering with. It could have some corrosion concerns. Okay. So again, not the be all end all, but it's just, that potential thing that we can look at to determine. So this is kind of getting into this. Basically, this is what we're talking about, that equivalent weight. You're taking the molecular weight of those compounds or those concentrations of those elements, whatever they might be, if that's chloride, sulfate, carbonate, or bicarbonate. And then you're getting down here, you're actually, calculating. If you follow these steps, you'll actually calculate out what those things are. And so the next slide kind of gets into that. If we have these concentrations of this, we would then get these equivalent concentrations or equivalent weights here. You would set it up in that equation and you get a 0.37. If you remember back to that slide, less than 0.8 would mean that it's unlikely to interfere with corrosion rates or unlikely to interfere with natural formation of scale. So that's a good range to be in. All right. What I want to get into here is calculating the 90th percentile. So you have 10 samples here of lead concentrations. How do you calculate that 90th percentile? Okay, so the first thing we want to do here is order those from lowest to highest. Okay, so you have sample 1 is a non-detect to 10 is now your highest at 122 parts per billion, or 0.122 milligrams per liter parts per million. All right, so order from highest to lowest. Then you're going to take your 90th percentile. So you have 10 samples. You're going to multiply that by 0.9 or 90%, right? To get 9. 9 is your equivalent of what that sample is. So we're going to be looking at the 9th sample here. Okay, so again, 10 samples here. 90% of those would be your 9th sample. We're going to be looking at that right here. There we go. 90th percentile is easy because we already have that sample taken. And so it's 70 parts per billion, 0.7. This is not in compliance. That would be an action level exceedance because that 90th is over 15 parts per billion. Okay. Problem 2 here gets a little bit trickier. This time we're looking at copper. That's not the part that makes it tricky. We're looking at, because now you have 21 samples. Okay, so you don't have that direct sample, the direct number of that 90th. Okay, so like the same way we take those copper values, you order from lowest to highest. So lowest being up here, highest being down here. Okay, you're going to take them. This time you're going to take that 21 samples. All right, you're going to multiply it by that 90% or 0.9, and you're going to get the 18.9th sample. Well, 18.9 doesn't exist. It's in between the 18th and the 19th sample, right? So it's somewhere in between 70 parts per billion and 98 parts per billion. All right. So what we got to do is what we call interpolation. So it's taking these values, you're taking between 70 and 0.9, or 70 and 98, or 0.07 and 0.098. You're going to multiply it by 0.9, which is your that 18.9th sample. Okay, this could be different. This isn't, it doesn't have to be 0.9 here because it's a 90th percentile. It could be 0.5 depending on how many samples you have, right? Okay, so I just want to clarify that 0.9 is not based on the 90th. It's based on whatever this result here is. Okay, that 18.9th sample. You're going to take those. You're going to take, your 0.9 of that in between these two, and then you're going to add it to that lower value. So it's going to be somewhere between that 70 and that 98, right? So what do we get for this value? 0.095. Well, yes, that's in between. So we checked our work. It works. Yes, it is in compliance because this is now a copper action level. So that means that our level is at 1.3 parts per million. Okay. So why collect 21 versus 20 samples? Well, maybe there's potential issues with sampling collection, invalid location or stagnation issues, uncertainty of the resident collecting sample, whether that's time or whatever else, or just the sample in general. So we always want to make sure that potentially if there's issues, we take another one so we can maybe exclude that or deal with that in the proper ways without then causing some more issues by not doing an additional sample. Why would you report 21 samples instead of just your 20, even though you're required to do 20? Well, you must report all valid sample results. Okay, so make sure you're turning your results into Eagle. Okay, so now we're just going to get into the miscellaneous stuff here. I'm going to kind of move through these because most of this stuff is a little bit older, and you should already probably know most of this. Okay, so lead-free definition under the Safe Drinking Water Act. Current rule prohibits installation or repair of any pipe, fitting, fixture, solder, or flux that does not meet the definition of lead-free. So make sure that if you're putting new fixtures in, new pipes, things like that, you're meeting that definition of lead-free. Again, you should already be knowing this because this came out, a while back. All right, so Reduction of Lead in Drinking Water Act of 2011. All right, this is what we're talking about, that change of definition to lead-free. It's not really lead-free, so that's just kind of an interesting word choice that we selected, but it is a reduction from where we were. Okay, so that reduction in actual percentage of weight that lead is, can kind of make up those materials, as well as, what's actually coming into surface with those wetted materials themselves. Okay, limiting that potential for lead risk or lead exposure. Okay. When in fact, January 4th, 2014, again, this has been in the works for a while, so you should already know it, you should already be doing it. What also came in at that time was that NSF 61 certification, making sure that your components are meeting those. But usually those things kind of go hand in hand with meeting that lead-free kind of stamp, as well as the NSF stamp 61 certified. Okay. Michigan's previous lead and copper rule. Again, you should already pretty much know all this stuff. We allowed a lot of things back in the day, but now we've gone through and we've changed them. So these are kind of the more updated things. So getting into the new lead and copper rule. So that 5% replacement requirements for lead service lines or galvanized previously connected to lead. Eventually, we're going to be lowering the action level for lead from 15 to 12 parts per billion. That's going to start January 1st of 2025. Creates a household advisory level of 40 parts per billion. Basically, it's that triggers that faster notice and educational materials for those homeowners. Triennial sampling is only for specific communities now that meet certain requirements. So most of the time you're going to be in that annual, unless you're really performing very well and you have very low lead and copper values, which is, you know, obviously what we're all trying to pursue, right? Also create a statewide advisory council to generate lead public awareness campaign materials, and going through that. Create local advisory councils in large communities, large cities, basically large meaning greater than 50,000 population. All right. So again, this is kind of an older thing here. We're already going through these. We should already have all these things set up. Additionally, we also have these requirements for the distribution system materials inventory. So you had the preliminary DSMI that was due January 1st, 2020. You also have January 1st, 2025, which is the actual complete DSMI. Okay, and I hope that you're all working towards that because there's been a lot of presentations on that as well. You had to update your sampling pools. You had to submit your sampling pools, make sure those are all appropriate. Again, we should be doing all of those things already. You have to use your highest results for your compliance tracking. You have to use your first fifth liter for the draw methods, and things like that. Okay. Change in source water treatment. This is a big one. If you're ever going through a source water change, you're drilling a new well, you're going through new chemical changes, even if it's a similar chemical to a similar chemical, we want to make sure that we're getting those permits in. If you're ever going through a treatment change, make sure that you are getting a permit in. All right. Really want to stress that. Okay. It's probably going to come with, you know, monitoring changes for lead and copper. We want to make sure we're not having these potential exposure events, corrosion events, because we're changing treatment or we're changing a source or things like that. Okay. And we want to make sure that we're monitoring during those times. So again, never change your corrosion control treatment, never change your treatment in general without approval from Eagle. Make sure that you're submitting your permits. Make sure you give ample time to give review and things like that. We want to make sure that you are not affecting your water quality because it can and does have an effect on corrosion control. Okay. Those passivation layers can be easily stripped. We can have issues with them. So please make sure that you're not going through any form of treatment, change or source water change, new wells, whatever that might be, interconnections. Make sure you're talking to Eagle first. I actually see that we have an error in here. I don't even know how that made it through, but that's DEQ. We are Eagle, Environment, Great Lakes and Energy, not Department of Environmental Quality. Okay. Make sure you're talking to us ahead of time. Talk to your district engineer. You can reach out to me for these treatment changes as well, because we do not want to have corrosion issues. Okay. I think that basically does it. So we'll open it for questions. It looks like I'm a little bit over, but go ahead, Matt.
Yeah, great job. Thanks, Matt. We do have one question in the hopper, and I'll read that to you. And while you're answering that, I'll bring up that final poll. But it says, why are we concerned with sequestering in the water column when we want to protect the pipe wall?
Why would you use sequestration? Well, if you have high iron content or manganese content, things like that, some communities want to have that form of treatment in there. Now, there's kind of two concepts. What are you looking to get done? Are you looking to have sequestration? Are you looking to get rid of iron? Or are you looking to have corrosion control treatment? You ideally, you would want, if you're looking for corrosion control treatment, you wouldn't want to sequester anything. You would want to have orthophosphate in there to build that passivation layer up. But if you're looking to sequester iron or manganese or something like that, you would want a polyphosphate. Okay, that doesn't necessarily have the same kind of effects on corrosion control treatment. Okay. hopefully that answered a question.
Yeah, thank you. For those of you that are still on, I just did start the final poll question. And that is corrosion control treatment plans can be changed as desired and do not require approval. This is a true false question. So remember, if you need continuing ed credits, make sure you do answer the poll questions. And that's all the current questions we have in the hopper at the moment.